The universe is running away from us faster than the laws of physics say it should. And the people telling you this are not cranks shouting from the edges of science. They are the most careful measurers our species has ever produced, holding instruments so precise they can weigh the light of a single dying star across 100 million light years. And when they compare their numbers to the predictions of the model that has ruled cosmology for a generation, the two refuse to match. Not by a whisper, not by the kind of rounding error that a second look would erase, by a gap wide enough that one of the most respected minds in the field stood before a room of his peers and instead of reaching for a gentle word, chose the sharpest one available. He called it a crisis. And then, the largest telescope humanity has ever flung into the dark opened its golden eye, and everyone expected it to smooth the trouble away. It did the opposite. It made the trouble deeper, stranger, and far harder to explain. If a mystery this size is the kind of thing that keeps you up at night the way it keeps them up, do us a small favor and hit like and subscribe. It genuinely helps more than you'd think. To feel why this matters, you have to understand what is actually at stake. For most of the last century, our picture of the cosmos rested on a single framework, a set of equations so elegant and so well tested that it earned a quiet reverence among the people who use it. Feed that framework the state of the infant universe, the conditions as they existed when everything was young and hot and nearly uniform, and it will carry those conditions forward across almost 14 billion years and hand you back the sky we see today. It predicted the faint background glow left over from the cosmos when it first turned transparent. It predicted the exact recipe of the lightest elements, the ratio of hydrogen to helium forged in the first minutes of existence. It predicted how galaxies would gather into vast webs and clusters stretched across distances the mind cannot hold. For decades it worked, and it worked so well that it began to feel less like a theory and more like a description of the way things simply are. And then the instruments got better, and the better they got, the more they started returning answers the framework insisted were impossible. It all comes down, in the end, to a single number. A number that sounds almost too modest to carry the weight now resting on it. It describes how fast space itself is stretching at this very moment, not in the distant past, not in some far future we will never see, but now, tonight, while you breathe. Look far enough into the dark, and every galaxy is drifting away from every other, carried apart not because they are flying through space, but because the space between them is swelling. Measure how quickly that swelling happens, and you have captured the pulse of the entire universe in a single figure. You would assume, reasonably, that in a cosmos governed by consistent and unbreakable laws, any two honest ways of measuring that pulse would land on the same value. That is the whole promise of science. Two teams, two methods, one reality, one answer. That promise is exactly what has broken. The first way of measuring reaches deep into the past, further back than almost anything else we can study. Long before there were stars, before there were galaxies, before there was anything we would recognize as structure, the universe was an opaque fog of particles and radiation. Then, when it had cooled just enough, that fog cleared in an instant, and the light that had been trapped inside it streamed free for the first time. That ancient light is still arriving. It fills the sky in every direction, stretched now into a faint microwave hum, the oldest signal in existence, a photograph of the cosmos taken when it was barely a few 100,000 years old. A spacecraft spent years mapping that hum with obsessive care, charting every subtle ripple in its temperature, every tiny variation in its brightness across the whole sphere of the sky. Those ripples are a fossil record of the seeds from which everything later grew. From them, physicists could read the precise physical state of the early universe, pour those conditions into the governing equations, and run the clock forward across the entire age of the cosmos to calculate how fast expansion ought to be proceeding right now. The number that came out was clean and confident, hedged by an almost impossibly small margin of doubt. Call it 67, in the unit's astronomers' favor. And they trusted it, because the map it came from is the most detailed portrait of the young universe ever assembled. The second way ignores the ancient past entirely. It measures the present directly, by climbing outward into the nearby universe one rung at a time, building a ladder of distances anchored in things we can see and touch with our instruments right now. The climb begins with a particular kind of star, a pulsing beacon that swells and dims in a slow, steady rhythm. What makes these stars extraordinary is that their rhythm is honest. The tempo of their pulsing is tied, with a reliability that borders on the miraculous, to how much light they truly pour out. Watch one blink, time its beat, and you know its real brightness. Compare that real brightness to how faint it looks from here, and the difference between the two gives you its distance with startling accuracy. These stars are the first rung. From there, astronomers reach for galaxies that host both these pulsing beacons and something far more violent, a specific breed of exploding star that detonates when a dead stellar core finally crosses a fatal threshold. These explosions are precious because they all flare to nearly the same peak brilliance, which means that once you have calibrated their true output using the pulsing stars in the same galaxy, you can recognize them from staggering distances and use them as mile markers stretching hundreds of millions of light years across the void. Chain the rungs together, measure how fast those distant galaxies are fleeing, and you arrive at your own value for the pulse of the universe. The team that has pushed this method to its limit, led by a physicist who already holds a Nobel Prize for helping discover that the expansion is speeding up at all, did not get 67. They got 73. 73 against 67. It sounds like a quarrel over nothing, the kind of small disagreement that rounds away on a bad day. It is not. In a discipline where the best measurements now routinely close in on the truth to within a single percent, a gap of 8 or 9% between two independent readings of the same fundamental quantity is a chasm. It is not a smudge on the lens. It shifts the estimated age of everything by more than 1 billion years. It changes the true size of the observable universe. It moves the moment when the first stars caught fire, when the first heavy elements were hammered together inside collapsing suns, when the raw ingredients for worlds and chemistry and living things first became possible. When you nudge that one number, you are not adjusting a dial. You are quietly redrawing the entire biography of existence, every chapter of it, from the first light to the ground beneath your feet. For a long stretch, most of the community assumed the fault had to lie in the latter. The framework was too successful, too deeply woven into everything else, to be the guilty party. The suspicion settled on those pulsing beacon stars, and it had a name and a plausible mechanism behind it. These stars tend to live in crowded, dusty places, the busy inner districts of younger galaxies where stars press shoulder to shoulder. When an older telescope aimed at one of them, its vision was not sharp enough to fully separate the beacon from its neighbors. The light of nearby stars leaked into the measurement, blending together, making the beacon appear brighter than it truly was. And a beacon that looks too bright is read as too close. Read the distances as too short across the whole ladder, and the calculated pulse comes out too fast. If that blurring was the culprit, then a keener eye would peel the crowded stars apart, correct the distances, ease the tension, and rescue the beloved framework. It was a comforting story. It let everyone imagine the crisis was really just a smudge waiting to be wiped clean. So the team did the decisive thing. They aimed the newest and most powerful eye ever placed in space directly at those very same stars. This observatory sits far from our planet, more than 1,000,000 kilometers out, well beyond the blur and shimmer of the air we breathe, in the cold and stable dark. Its enormous mirror, coated in gold and folded like origami to fit inside its rocket, drinks in infrared light with a sensitivity that makes every earlier instrument look like a foggy window. It can slice through cosmic dust. It can separate stars that older cameras hopelessly smeared into a single blob. Much of the field genuinely expected this new eye to be the peacemaker. Its superior vision would expose the blending, tighten the distances, and coax the stubborn number back into agreement with the ancient light prediction. Some people were, by their own admission, already composing the quiet farewell to the whole controversy before the fresh data even arrived. They were sure the sharper view would dissolve the problem the way sunlight burns off morning mist. The sharper view did nothing of the kind. It looked at the crowded beacons, separated them cleanly, measured them with a precision no one had ever achieved, and returned almost exactly the same distances as before. The blending, it turned out, had not been fooling anyone in the way the hopeful story required. The pulse held at 73. When the results were gathered and published, they covered a whole set of host galaxies, a spread of exploding stars, and a great many individual beacon stars reaching out to a galaxy more than 100 million light-years away. And the verdict was blunt. Measurement error could be ruled out with overwhelming confidence. The discrepancy was not a mistake in the latter. It was real. And the physicist leading the effort framed what remained with the careful gravity of someone who chooses each word to carry exactly its true weight. Once you have eliminated the errors, he said in effect, what is left standing is the possibility that we have simply misunderstood the universe. There is a moment that has since become part of the lore of this whole affair. At a gathering of theorists, that same physicist turned to another Nobel laureate, one of the great figures of particle physics, and asked him plainly whether the field ought to start calling this thing a problem. The older man shook his head. Don't call it a tension, he said. Don't call it a problem. Call it a crisis. And that word, spoken by someone with nothing left to prove and no incentive to exaggerate, has clung to the subject ever since. Because it is honest. Something in the foundation is not holding, and the people closest to the foundation can feel it shifting. But before you conclude that the old framework is simply finished, and we are back at the beginning with nothing, understand that the truth is more tangled, and in a way, far more interesting than a clean defeat. Not everyone even agrees that the tension is as settled as the 73 camp believes. Another astronomer, one who has spent a career building her own version of the distance ladder, deliberately designed hers to lean less on those crowded, blending-prone beacon stars. Her approach reaches instead for other reliable markers, ancient red giant stars in the calmer outskirts of galaxies, and a separate class of luminous stars found far from the crowded cores, both of them much harder to confuse with their neighbors. When she turned the new space telescope on her own carefully chosen targets, her methods did not all agree with each other. Some of them landed near 68 or 70, comfortably close to what the ancient light predicted. Another came in higher, closer to the 73 camp, but with wider uncertainty. Her combined answer sat in an awkward middle ground, a kind of no man's land between the two warring numbers, refusing to fully commit to either side. And here is the detail that ought to make you sit up. When another Nobel-winning cosmologist reviewed her results, he pointed out something quietly unsettling. The disagreement, he noted, might be lurking inside the star-based measurements themselves, before you even bring the ancient light into the comparison. That is a different and deeper kind of trouble. It suggests that the distance ladder, the very tool astronomers have leaned on for 100 years to chart the nearby cosmos, might have unresolved flaws buried at its base, cracks that no single telescope, however powerful, can simply mend. The leader of the 73 team pushed back hard, arguing that his rival's sample of exploding stars was too small and possibly skewed in a way that dragged her numbers downward. The clash between these two teams, both brilliant, both painstaking, both staring at the identical sky through the identical instrument and walking away with different answers, has become one of the most closely watched rivalries in all of modern science. And sitting at the dead center of it is a question the reigning framework simply cannot answer with the pieces it currently owns. If the universe truly is stretching faster than our finest model predicts, then what, exactly, is pushing it? One idea keeps rising to the surface, tentative and unproven but stubbornly attractive. Imagine that in the first flicker of cosmic history, in the earliest few 100,000 years, there was an extra ingredient, a brief and mysterious surge of outward pressure that flared into being and then faded away almost without a trace. If something like that really happened, it would have subtly rewritten the conditions of the young universe, just enough to lift the ancient light prediction upward towards 73, without shattering the many other things the framework gets gloriously right. One theorist who helped shape this notion has likened it to the newborn cosmos receiving an unexpected shove, a single push in its first moments, whose consequences would ripple forward across every billion years that followed, altering the very rate we measure today. Nobody has caught this surge in the act. No experiment has confirmed that it ever existed, but it remains one of the very few proposals on the table that could reconcile the two numbers without tearing down the parts of the model that still perform brilliantly. It is a patch, an elegant guess, and the fact that the field is entertaining it so seriously tells you how badly the standard story needs help. Now, the runaway expansion would have been enough on its own to rob a generation of cosmologists of sleep. But the great new eye in the dark was not finished. Almost the instant it began peering into the deep past, it found things that, by every rule the framework laid down, had absolutely no right to exist. When you look far enough away, you are also looking far enough back in time, because the light has taken so long to reach you. And so this telescope, gazing across nearly the whole width of cosmic history, was seeing galaxies as they were just a few 100 million years after the beginning, in an era the model insisted should contain only faint, fragile, half-formed infants, small smudges of stars barely holding themselves together. Instead, it found monsters. It found galaxies already grown massive, some of them carrying as much starlight as our own vast home galaxy, blazing at us from a time when the universe was a small fraction of its present age. A galaxy that took our own neighborhood the better part of 14 billion years to assemble appeared to have thrown itself together in under a billion. It was as if you had photographed a newborn and found a full-grown adult staring back. One astronomer ran the brutal arithmetic on the earliest and heaviest of these candidates, and discovered that several of them were pressed right up against the absolute ceiling of what the framework could permit. To build galaxies that heavy that quickly, nearly every single atom of ordinary matter available in their surroundings would have had to collapse into stars, converting raw gas into suns with almost perfect ruthlessness. In an ordinary, well-behaved universe, that conversion is wasteful and slow. Only around a tenth of the available gas ever becomes stars at all. The rest gets too hot, gets blown back out by the fury of radiation, or simply drifts, unused, for ages. These early giants looked like they were running at nearly total efficiency, a cosmic factory converting every last scrap of raw material into finished product with no waste whatsoever. The framework had no gear that turned that fast. The first reaction, by many honest accounts, was something close to alarm. If galaxies this large truly assembled this fast, then either our understanding of how galaxies are born was gravely incomplete, or the framework itself needed surgery at its very core. Some theorists began wondering aloud whether unknown particles or forces had prowled the early universe and hurried star formation along faster than anything the equations could produce. Then came a twist that reshaped the picture, without ever fully dissolving the mystery. A careful re-examination of the data, led by a young researcher, found that many of these apparently monstrous galaxies had been badly misread. A number of them were compact, intensely reddish specks, nicknamed for their appearance as little red dots, and hiding at the heart of each was not simply a vast crowd of stars, but a supermassive black hole feeding, with terrible appetite on the gas swirling around it. The friction of all that matter spiraling inward toward oblivion generated ferocious heat, and that heat blazed outward as light so intense, it blended seamlessly with whatever starlight the galaxy actually held. From billions of light years off, a galaxy with a ravenous black hole at its core looked nearly identical to a galaxy with 10 times as many stars. The black hole's glow had been masquerading as an ocean of suns. Strip those little red dots out of the tally, and many of the remaining galaxies settled back down into something the framework could just barely stomach. One senior astronomer put it flatly. "There is no crisis from the galaxies," he said. At least not from the galaxies. But the relief was not total, and the story refused to close cleanly. Even after the deceptive red dots were removed, roughly twice as many genuinely massive galaxies remained in that early epoch as the framework had any right to expect. Not enough to snap the model in half, enough to bend it, and to keep bending it, and to leave a persistent ache where the numbers refused to fully cooperate. And then the great eye found something that troubled the theorists in an entirely different way. Something that should have been impossible in a young and violent cosmos. It found a grand spiral, a galaxy with sweeping, orderly arms wound elegantly around a bright center, already fully formed within the first couple of billion years of everything. Spiral structure is supposed to be a mark of maturity and patience. It emerges from calm, gradual, undisturbed growth, the sort of slow and gentle evolution that ordinarily takes many billions of years to sculpt. It is not what you expect from an era the theorists imagine as a chaos of violent collisions and endless mergers, galaxies crashing and tearing at one another in the dark. Yet there it was, serene and structured, in a time that had no business producing such a thing. The astronomer who helped find it noted that the galaxy had either gathered its enormous mass in an unusually orderly fashion, or had made most of its stars right where they sat, without the brutal collisions that normally build the giants. Either explanation is a quiet rebuke to the standard picture of how structure grows. And the plot only thickened, because a separate team using the same telescope studied hundreds of galaxies from that identical early stretch of time, and found the exact opposite. Most of them were turbulent, lumpy, disordered messes that had not yet settled into smooth, spinning disks. So the young universe, it seems, held both things at once: raucous, half-built adolescence thrashing toward form, and at least one poised, mature spiral gliding calmly among them. In the very same era, the framework does not handle that coexistence gracefully. It expects a tidy progression from chaos to order, and instead it is being handed a scene where both are already present, side by side, long before the schedule allows. Then there is the matter of the shapes themselves, which is stranger still. A study that gathered researchers from several of the world's leading institutions examined a great many of these early galaxies and found that a surprising number of them were not rounded or disc-like at all. They were stretched, elongated, drawn out into long, slender forms like cosmic grains of rice or cigars adrift in the dark. Those elongated shapes do not sit comfortably with the standard assumption about what the invisible scaffolding of the universe is made of. For a quarter century, cosmology has been built on the idea that most of the matter in existence is a cold, slow, clumping kind of unseen substance that gathers into compact, roughly spherical halos, and galaxies form nestled inside them. But long, drawn-out galaxies fit more naturally with alternative pictures. Ones in which the invisible matter is lighter, or behaves more like a wave, smoothing the great filaments of the cosmic web, so that gas and stars flow along them in stretched-out streams, rather than balling up into tidy spheres. That distinction matters far more than it might first appear, because that unseen substance is not merely one ingredient among many. It is the scaffolding on which everything else is hung. It decides where galaxies form, how they gather into clusters, how the largest structures in all of creation are strung across the sky. Change its nature, make it a little lighter, or let it behave in some subtle way our experiments have not yet caught, and the consequences ripple outward through nearly every prediction the framework makes. It would alter how much a galaxy cluster ought to weigh. It would shift how many small companion galaxies should be swarming around the large ones, a count that has itself been a nagging sore point for years. It would change how the gravity of massive objects bends and warps the light passing near them. You cannot quietly swap out the foundation of a building and expect the walls to stay exactly where you left them. And there is yet another fracture, one that draws far less attention than the runaway expansion, but may in the end prove just as important. It concerns how clumpy the universe is on the grandest scales, how strongly matter has gathered itself into knots and voids across the vast reaches of space. The framework predicts a specific amount of this clumping. When astronomers measure it directly, by weighing the distribution of matter through the way it bends distant light, and by charting how galaxies cluster, they keep finding slightly less clumping than the model demands. The universe is a touch smoother, a shade less lumpy, than the equations insist it should be. The leader of the 73 team has described this as the little sibling of the expansion problem. Quieter, less discussed in public, but worth watching with real care. Because if both of these tensions turn out to be genuine and independent, they may not be two separate ailments at all. They may be two symptoms of a single deeper illness, two cracks spreading from the same hidden fault, running somewhere beneath the whole structure. So where does all of this leave the framework that ruled cosmology for so long? Not dead. That has to be said plainly, because the temptation to declare a revolution is strong, and the truth is more disciplined than that. The old model still explains the ancient background glow with breathtaking precision. It still predicts the cosmic abundances of the lightest elements, with an accuracy that feels almost unfair. It still accounts for the sweeping arrangement of galaxies across scales that no rival framework has come close to matching. Nothing else in the running can touch its overall record. But it is developing fractures that simply were not visible a decade ago. Fractures that stubbornly refuse to close as our instruments sharpen. Fractures that, if anything, grow cleaner and more defined the better we manage to see. The expansion problem will not resolve itself. The early universe keeps handing us galaxies too large, too structured, and too strange for any model to have foreseen. The nature of the invisible matter that makes up roughly a quarter of all that exists may not be what we have spent 25 years assuming, and the mysterious outward pressure responsible for most of the universe's contents, and for the accelerating stretch of space, remains a placeholder, a name we have given to something we cannot identify, cannot measure directly, and cannot explain with any physics we currently hold in our hands. The physicist at the heart of it chose his words with his usual precision when he spoke about all this. The gap between how fast the universe is actually expanding and what the framework predicts, he said, suggests that our understanding may be incomplete. Two of the greatest observatories ever built now confirm each other's findings. We have to take this problem seriously. And what is genuinely remarkable about this moment in the long history of the subject is that the mood is not despair. Nobody is panicking. The feeling among the people closest to it is closer to the strange thrill of working a vast puzzle for years, growing quietly confident that you finally understand the picture forming under your hands, and then lifting a single piece and discovering that it does not fit anywhere in what you have already built. That does not mean the whole puzzle is wrong. It means the image printed on the box may not be the complete scene. There is more picture than you were promised. And the tools that will decide the matter are already on their way. New observatories are being prepared to survey enormous swaths of sky expressly, to study that mysterious outward pressure, and trace how its behavior has changed across cosmic time. Others are already mapping the raw geometry of the universe on a scale no telescope has ever attempted, charting the shapes and distances of countless galaxies to see whether the invisible scaffolding behaves as the framework demands. Future measurements will let astronomers pin down the distances to those pulsing beacon stars using pure geometry, the cleanest possible ruler, stripping away one more potential source of hidden error. Ground-based instruments have already produced the most detailed map yet of the ancient background glow, and it nudged the old prediction a hair upward, though nowhere near enough to close the gap. The data keeps pouring in, the picture keeps sharpening, and it stubbornly refuses to simplify. It is worth remembering that cosmology has stood at a cliff like this before, and lived to tell it. There was a time, not so many decades ago, when the numbers seemed to insist that the universe was younger than the oldest stars glowing inside it, which is a flat impossibility, a contradiction that struck at the root of everything. A star cannot be older than the cosmos that contains it. For a while it looked as though something fundamental had to be broken beyond repair. And then came the discovery that the expansion of the universe was not slowing down as everyone assumed, but speeding up, driven by a form of energy no one had suspected. And in an instant the whole tangled picture snapped into a new and sharper focus. What had looked like a fatal wound in our understanding turned out to be the shadow of something enormous that no one had yet learned to see. That is the recurring shape of these episodes. They arrive dressed as endings. They almost always turn out to be doors. Right now, somewhere in the immense gulf between what the young universe looked like and what we see wheeling around us tonight, in those billions of years of history we have never watched unfold in full, something is happening that we do not yet understand. Some ingredient has gone uncounted. Some process has gone unmodeled. Some quiet property of space and time has never yet been imagined by anyone who ever sat down to write equations about the world. And the great eye in the dark keeps staring into that gap with the clearest vision our species has ever built, finding things that were not supposed to be there, confirming numbers that were not supposed to hold, and telling us, one patient observation at a time, that the universe we thought we had mapped so completely is under no obligation whatsoever to match the map. That is not a failure of science. It is science doing precisely what it was made to do, walking straight up to the edge of what it knows, and refusing to turn back. And whatever eventually accounts for all these fractures at once, whatever revision or upheaval, finally makes sense of the runaway expansion and the impossible galaxies and the invisible scaffolding. It will not shrink the universe or make it more ordinary. It will make it stranger than the story we tell today. And if the whole history of this science is any guide at all, it will also, in the end, make it more beautiful than anything we have yet dared to draw. To understand just how far the ground has shifted, it helps to sit for a moment with what that ancient glow actually is, because almost nothing else in science reaches so far back and returns with such clarity. Picture the universe in its infancy. Not the blazing chaos of the first instant, but a slightly later time, when everything had cooled from an inferno into a dense, uniform fog. In that fog, light could not travel freely. Every time a ray tried to move, it slammed almost immediately into a charged particle and scattered, the way headlights vanish into thick mist. For hundreds of thousands of years, the whole cosmos was opaque, glowing, and impenetrable. A wall of light with nothing able to escape it. Then the temperature crossed a threshold. The particles joined into neutral atoms, and in a single sweeping moment across the entire universe, the fog lifted. Light was suddenly free to travel, and it has been traveling ever since, stretching along with the swelling of space until its once fierce glow cooled into the faint microwave whisper we detect today. When we map that whisper, we are not looking at a picture of the early universe. We are looking at the actual light, the very same photons, arriving after a journey of nearly the entire age of existence. It is the closest thing to a direct photograph of the cosmic dawn that we will ever possess. And every prediction of the reigning framework is anchored to the exquisite patterns hidden within it. The astonishing thing is how much information those patterns hold. The tiny fluctuations in that ancient light, differences in temperature smaller than 100,000th of a degree from one patch of sky to the next, are the frozen imprint of sound. In the hot early universe, pressure and gravity fought each other, and their struggle set the entire cosmos ringing like a struck bell, waves of compression rolling through the primordial plasma. When the fog lifted, those waves were caught mid-motion, their crests and troughs printed permanently onto the sky as slightly hotter and slightly cooler regions. By measuring the sizes and spacings of those frozen ripples with painstaking care, physicists could deduce the ingredients of the universe with a precision that would have seemed like fantasy a generation earlier. How much ordinary matter? How much of the invisible clumping substance? How much of the mysterious outward pressure? The geometry of space itself. All of it read from the faint music of a universe that sang before there were stars to hear it. This is why the 67 has such authority behind it. It does not rest on a single fragile assumption. It rests on the entire self-consistent story that this ancient light tells. A story that has passed test after test after test. Which is exactly why its disagreement with the latter is so hard to wave away. And the latter deserves the same respect, because it too is a triumph of stubborn ingenuity, built across more than a century. The people who first realized that certain pulsing stars kept honest time did not have space telescopes or digital sensors. They compared photographic plates by eye, counting the slow brightening and dimming of stars in distant star clouds, and noticed a pattern so regular it could be trusted as a ruler. That single insight became the foundation on which the measured size of the universe was first built. Every rung added since has been an act of careful calibration, each one checked against the one below it, each one extending the reach of the measurement a little further into the dark. The exploding stars that mark the upper rungs are among the most violent events in all of nature. The death throes of stellar cores releasing in a few weeks more light than our own sun will pour out across its entire lifetime. That they should also be dependable mile markers, flaring to nearly the same brilliance every time. is one of those quiet gifts of physics that makes cosmic measurement possible at all. The latter is not a guess. It is a structure of interlocking evidence. And the fact that it now points so firmly to 73 is precisely why the tension cannot be dismissed as sloppiness. There is a human dimension to all of this that rarely makes it into the equations. And it is worth pausing on. Consider what it means to spend years of your life chasing a single number, aiming the most expensive and sophisticated machine ever built toward faint smudges of light, refining, checking, arguing, only to arrive at an answer that does not fit the world you were taught. The temptation, in that position, would be enormous to nudge the result, to find the error you were expected to find, to bring your number quietly into line, and spare yourself the storm. It takes a particular kind of discipline to instead hold the uncomfortable answer up to the light and say, plainly, this is what the sky is telling us, even if it breaks the story we love. That discipline is the real engine of this entire drama. The two rival teams, locked in their long and public disagreement, are not enemies. They are both refusing, in their own way, to let the universe be simpler than it actually is. And that refusal, that willingness to sit inside the discomfort, rather than paper over it, is exactly what has kept the crisis alive long enough for the rest of us to notice it. What makes the impossible early galaxies so haunting is that they touch something deeper than a single number. They ask how quickly the universe was able to organize itself, how fast raw gas could gather and ignite and build the great luminous islands we call galaxies. The framework contains an entire choreography for this, a slow dance in which the invisible matter clumps first, pulling ordinary gas into its gravitational wells, where the gas cools and settles and finally collapses into stars over long stretches of time. That choreography has a rhythm, and the rhythm has limits. There is only so much gas, and it can only fall inward and cool so fast. To find fully grown galaxies blazing at us from the first few 100 million years is to find dancers who have somehow completed a routine that should have taken the whole night, before the music had barely begun. Even with the deceptive black hole glows removed from the count, the remaining excess of massive early galaxies whispers that the choreography may be incomplete, that the universe found ways to build itself faster than our understanding allows. Some of the proposed explanations are almost as strange as the problem. Perhaps the very first generation of stars was different from anything alive today, monstrous and brilliant, forming in bursts of ferocious intensity that converted gas into light far more efficiently than the gentle star formation we see around us now. Perhaps those first stars lived fast and violent lives, seeding their surroundings with heavy elements and stirring their galaxies into rapid growth. Perhaps the invisible scaffolding gathered more quickly, or in different shapes, than the cold and clumping picture predicts, giving ordinary matter a head start it was never supposed to have. Each of these ideas nibbles at a different corner of the framework. None of them yet fits every observation at once. And that is the honest state of things. A scatter of promising fragments, no single one of which has grown into a full replacement. All of them circling the same stubborn realization that the early universe was more productive, more precocious, and more surprising than the equations foretold. The elongated shapes carry their own quiet weight in this. Shape, in cosmology, is a fingerprint of the forces that molded an object, and the shapes of the earliest galaxies are a fingerprint of the scaffolding they grew within. If that scaffolding were the cold, heavy, clumping substance the framework assumes, the earliest galaxies should tend to gather into rounded, compact forms, cradled in roughly spherical wells of invisible matter. Finding so many of them stretched into long, slender streaks suggests instead that they may have formed strung along the great filaments of the cosmic web, flowing like beads on a thread, rather than pooling into balls, and filaments that smooth and continuous point toward a different kind of invisible matter, one that is lighter or gentler or wave-like in its behavior, one that does not fragment into as many tiny compact clumps. If that turns out to be right, it would not merely adjust a detail. It would revise the identity of the most abundant form of matter in the universe, the very substance whose gravity built the scaffold on which every galaxy, including our own, was raised. It is tempting, standing in the middle of so many cracks, to imagine the whole edifice collapsing at once into rubble. But that is not how these things go, and it is not what the evidence suggests. The far more likely truth is subtler and, in its way, more thrilling. The framework is probably not wrong so much as unfinished, a superb approximation that captures the broad sweep of cosmic history with astonishing fidelity, while quietly missing some ingredient that only reveals itself at the finest levels of precision. Precision we could not reach until the current generation of instruments came online. For most of the last century, our measurements were too coarse to feel the missing piece. Now they are sharp enough to feel it everywhere. In the runaway expansion, in the precocious galaxies, in the elongated shapes, in the faint deficit of clumping. And a missing ingredient that shows up in that many independent places is not noise. It is a clue, repeated over and over, insisting that we listen. The people doing this work know they may be standing at the threshold of something as large as the discovery that the expansion of the universe is speeding up. A revelation that reorganized cosmology within a few short years and rewrote the textbooks so thoroughly that a whole generation grew up taking it for granted. They also know it might take decades to see the full shape of what is coming, that the answer might depend on instruments not yet finished and ideas not yet imagined. That uncertainty is not a burden to them. It is the entire attraction. To live in a moment when the map and the territory have visibly parted ways, when the sky is refusing to obey the story we told about it, is to live in one of the rare intervals when the deepest questions are genuinely open again, when the next great reframing of reality has not yet been written, and could, in principle, be glimpsed by anyone patient enough to keep looking. And so the watching continues, night after night, in the cold and stable dark beyond our atmosphere, and in the quiet rooms where the data is turned over and argued about. The great eye gathers ancient light and hands it to us stretched and reddened by its long journey. The rival teams sharpen their ladders and defend their numbers and refuse to blink. New observatories are readied to survey the invisible geometry of everything, and underneath it all runs the single, patient, unanswered question that has turned a quiet corner of science into one of the most electric frontiers of our time. Why is the universe running faster than it should? And what is the thing we have not yet seen that is making it do so? We do not know. Not yet. But the not knowing is not a wall. It is an opening. The same kind of opening that has, again and again across the history of this science, led not to a smaller and duller cosmos, but to one vaster and more astonishing than the one we thought we understood. The universe we mapped so confidently is showing us, gently and relentlessly, that it is larger than our map, and there are few more thrilling things a person can be alive to witness than a map of everything being redrawn in real time, by hands careful enough to admit they were wrong, and eyes clear enough to see what comes next. It is worth lingering on what that runaway number would actually do to the story of everything, if the higher value proves true, because the consequences are not abstract. A faster expansion today implies a universe that reached its present size more quickly, which means less time has elapsed since the beginning than the slower number suggests. Shave 1 billion years or more off the age of the cosmos, and you are not merely editing a figure in a table. You are compressing the entire timeline in which the first stars had to ignite, in which the first galaxies had to gather, in which generations of suns had to live and die to forge the heavier elements that make planets and oceans and living chemistry possible. The oldest stars we can find, ancient and metal-poor, glowing faintly in the outskirts of our own galaxy, have their own estimated ages, and those ages cannot exceed the age of the universe that contains them. If the cosmos is younger than we thought, the margin between the oldest stars and the birth of everything grows uncomfortably thin. It is precisely the kind of squeeze that has, in the past, signaled that a piece of the picture is missing. The expansion problem, in other words, does not sit in a sealed room. It leans on the walls of every other chamber in the house, and the deeper you look into how that expansion is measured, the more you appreciate why the disagreement has been so difficult to dismiss. The two methods are not merely different techniques aimed at the same target. They are separated by nearly the entire history of the universe. One reads the pulse from the faint imprint of the cosmic dawn and carries it forward across billions of years through the machinery of the model. The other reads the pulse directly from the nearby, present-day cosmos, without ever invoking the deep past at all. In a sense, one is a prediction, and the other is an observation. And for most of the history of the subject, the two agreed closely enough that no one worried about the seam between them. It was only when both were pushed to extraordinary precision that the seam split open. The prediction says one thing about how fast space should be stretching now. The direct observation says another, and the gap between them is, in the most literal sense, a gap between the universe's youth and its old age, a discrepancy that seems to grow out of the passage of cosmic time itself. Something, it whispers, happened in between. Something the model does not contain. That single word, between, is where much of the theoretical energy now flows. The framework describes the beginning through the faint ancient light with tremendous success, and it describes the present through the latter with tremendous success, but the two descriptions do not connect smoothly, and the trouble may live in the vast unwatched middle. Almost nothing in that middle stretch of cosmic history has been observed in complete detail. We have the snapshot of the dawn, and we have the nearby present, and between them lies an enormous span we reconstruct largely through the model, rather than through direct sight. If a hidden ingredient acted during that span, subtly altering the rate of expansion at some point along the way, it could pull the two numbers apart exactly as we see. This is why the idea of an early extra push has been so seductive to theorists, and why others have proposed pushes at later times instead, or changes in the behavior of the mysterious outward pressure as the universe aged. Each proposal is an attempt to fill the unwatched middle with something that reconciles the beginning and the end. None has yet won the argument, but the shape of the search is clear. Find the missing actor in the middle of the play, the one whose entrance and exit we never recorded, whose presence would explain why the first act and the final act no longer quite agree. The impossible galaxies deepen this sense that the middle chapters were livelier than we wrote them. Consider what it means to look at an object whose light left it when the universe was a small fraction of its present age. That light has crossed almost the entire span of cosmic history to reach the great mirror waiting for it in the dark. When it finally arrives, stretched and reddened by the swelling of space along the way, it carries a portrait of a moment we have no other means of witnessing, and the portraits kept coming back wrong, or rather, wrong according to the schedule the model had drawn. Galaxies were supposed to build slowly, brick by brick, small clumps merging into larger ones across long ages. Instead, the telescope kept finding grand accumulations of stars already assembled in eras that should have held only scattered beginnings. It was as though we had opened a photo album expecting to see a construction site, and found the finished cathedral instead, complete and gleaming, generations ahead of schedule. The correction involving the disguised black holes was real and important, and it rescued a great deal. But it is worth being honest about what it did and did not do. It explained why some of the very brightest early objects had seemed impossibly heavy. Their brilliance came partly from matter screaming inward toward a black hole, rather than entirely from stars. So we had overestimated how many stars they held. That is a genuine and satisfying resolution for a chunk of the puzzle. But it did not erase the surplus entirely. When the disguised objects were set aside, there were still more massive galaxies in the early universe than the framework comfortably predicted. And there was still at least one grand and orderly spiral gliding through an age that was supposed to be all violence and disorder. And there were still those strange, elongated forms stretched along the invisible filaments of the young cosmos. The black holes trimmed the mystery. They did not close it. And the part that remains is arguably the more interesting part, because it cannot be blamed on a trick of measurement. It seems to be telling us something true about how quickly and how tidily the early universe was able to organize itself. And that truth does not match the story on the page. There is something almost poetic in the fact that black holes of all things turned out to be hiding inside the mystery. These are the darkest objects in existence, regions where the pull of gravity grows so overwhelming that not even light can climb back out. And yet, in the young universe, they announce their presence through blazing beacons of radiation. The glow of matter heated to unthinkable temperatures as it spiraled toward the point of no return. A feeding black hole is one of the brightest things the cosmos can produce, precisely because of how violently it consumes. And in the early universe, these beacons were common enough and brilliant enough to masquerade as entire populations of stars, fooling our first count of the deep past. That such profound darkness should reveal itself through such extraordinary light is one of those paradoxes that makes this subject endlessly compelling. It is also a warning, humbly delivered, about how easily the deep universe can deceive an eye that has never seen it before at this clarity. We are, in a real sense, learning to read a language we have only just begun to hear spoken. The question of the invisible matter deserves its own long look, because it is perhaps the strangest admission at the heart of modern cosmology. When we add up all the matter we can see, all the stars and gas and dust in all the galaxies, it accounts for only a small fraction of the gravity we actually observe holding those galaxies together and steering their motions. Galaxies spin far too fast to survive on the pull of their visible contents alone. By rights, they should fling themselves apart. Clusters of galaxies swarm with far more energy than their visible mass could contain. Something unseen is supplying the missing gravity. Something that neither emits nor absorbs light. Something we detect only through its pull. For decades, the leading assumption has been that this unseen substance is cold and slow. A swarm of sluggish particles that gather readily into compact clumps, seeding the wells into which ordinary matter falls to form galaxies. That assumption is the scaffolding of the entire framework. And it has worked remarkably well on the largest scales, reproducing the grand web of galaxies with impressive fidelity. But the framework has long had troubles on smaller scales. Troubles that predate the newest telescope by many years. The cold and clumping picture predicts that large galaxies like ours should be surrounded by great swarms of small companion galaxies. Far more than we actually observe. It predicts certain patterns in the dense centers of galaxies that the observations do not cleanly match. These have been persistent irritations, quietly noted, never quite resolved. And now the elongated shapes of the earliest galaxies have added a fresh irritation from the opposite end of cosmic time. If the unseen matter were lighter, or warmer, or behaved like a wave rather than a swarm of cold particles, several of these irritations might ease at once. the small companion galaxies would be fewer, because a gentler form of unseen matter would not fragment into as many tiny clumps. The early galaxies would form in stretched-out streams along smoother filaments, producing exactly the elongated shapes that were observed. The pieces begin, tantalizingly, to fit a different picture. But changing the nature of the unseen matter is not a small edit. It touches everything, and the very success of the cold picture on the largest scales means any replacement must preserve that success while curing the ills below. No proposal has yet threaded that needle completely, but the needle is there, and more hands are reaching for it. The quieter tension, the one concerning how clumpy the universe is, reinforces the sense that the trouble is not confined to a single measurement. Across enormous volumes of space, matter has gathered itself into a vast cosmic web, dense filaments and knots surrounding immense empty voids. The framework predicts precisely how pronounced that clustering should be, how sharp the contrast between the crowded regions and the barren ones. And when astronomers weigh that contrast, chiefly by measuring how the gravity of all that matter subtly bends the light of galaxies behind it, they keep finding the universe slightly smoother than predicted, the clustering a little gentler than the equations require. On its own, this might be shrugged off as a minor mismatch, but it sits alongside the expansion problem, and the two together raise a disquieting possibility. What if they are not separate at all? What if a single unseen ingredient, or a single flaw in our picture of the unseen matter and the mysterious outward pressure, could produce both the runaway expansion and the missing clumpiness at once? Two symptoms, one disease. That is the kind of connection that makes theorists lean forward, because a single cause that explains multiple anomalies is exactly the signature of a real discovery, rather than a scatter of unrelated errors. None of this means the people doing the work are lost. If anything, they are exhilarated, because they understand the pattern they are living inside. The history of their science is a history of exactly this: long stretches of confident consolidation, when the framework seems to explain everything, and the main task is refinement, punctuated by sudden intervals, when the measurements outrun the theory, and the whole picture trembles. Every one of those trembling intervals, in the past, resolved not by discarding everything that came before, but by adding something profound that had been missing, something that, once seen, made the old confusion snap into sense. The realization that the cosmos is filled with unseen matter was one such addition. The realization that its expansion is accelerating was another, and it arrived precisely when the numbers seemed most hopelessly tangled. Each time, the crisis felt total, and each time it turned out to be the outline of a discovery pressing against the limits of what could then be measured. The people watching the current fractures know they may be living through another such moment. And there is a particular kind of joy in that knowledge, the joy of standing at a frontier that is genuinely open, where the next chapter has not been written, and the sky itself is dictating the terms. Consider, too, how much of this drama depends on instruments that did not exist a generation ago, and how much it will depend on instruments that do not exist yet. The precision that revealed the expansion problem is the fruit of decades of engineering, of learning to place mirrors beyond the atmosphere, to cool detectors, to within a whisper of absolute cold, to separate the light of individual stars in galaxies, impossibly far away. Every increase in sharpness has been an increase in our ability to feel the missing piece. And the next generation is already taking shape. Observatories are being built and prepared that will survey the sky on a scale that dwarfs everything before them, cataloging not thousands but millions of galaxies, mapping the invisible geometry of the cosmos with a thoroughness that will either confirm the framework in exquisite detail or expose its fractures beyond any hope of patching. Some of these instruments are designed expressly to study the mysterious outward pressure, to measure whether it has been constant across cosmic time, or whether it has changed, which is one of the deepest questions of all. If that pressure turns out to vary, to strengthen or weaken across the ages, it would rewrite the far future of the universe, as thoroughly as it would rewrite the past. And that far future is worth contemplating, because the answer to the expansion problem will shape it profoundly. If the mysterious pressure is constant, the universe faces a long, cold, ever emptier future. Galaxies drifting apart until the sky beyond our own island of stars fades slowly from view over unimaginable spans of time. If that pressure grows stronger, the ending could be more violent, the expansion accelerating without limit. If it weakens, the story changes again. The number at the center of the current crisis is not only a key to the past, it is a hinge on which the entire destiny of the cosmos turns. When we argue over 67 versus 73, we are, without quite saying so, arguing over how the universe ends and how much time everything has. That is the hidden gravity beneath these dry-seeming measurements, the reason the people who make them speak with such careful intensity. They are not merely refining a figure. They are trying to read the final pages of a book that has not finished being written. There is a temptation, faced with mysteries this vast, to feel small, and it is worth resisting that temptation in favor of something more accurate. Yes, the scales involved are beyond human intuition. Distances measured in millions of light years, spans of time measured in billions of years, quantities of matter and energy that dwarf anything we will ever hold. But the remarkable thing is not our smallness. It is that a species confined to a single small world, with lifespans of a few decades, has managed to measure the pulse of the entire universe two different ways: to photograph the light of the cosmic dawn, to weigh galaxies whose light set out before our planet existed, and to notice, in the fine disagreement between two numbers, that our understanding of everything is incomplete. That is not smallness. That is one of the most extraordinary achievements any collection of minds has ever accomplished. And the fact that it has led us to the edge of our knowledge, rather than to a comfortable resting place, is not a defeat. It is the whole point. The measurements were never meant to make us comfortable. They were meant to tell us the truth. And the truth, right now, is that the universe is stranger than our finest theory. And it is inviting us to look again. So the great eye keeps watching, patient and unblinking, in the cold beyond the sky. It gathers the ancient light and the light of impossible galaxies, and the faint glow of matter falling into darkness, and it hands all of it to the careful minds waiting below. Those minds sharpen their ladders and defend their numbers and argue in good faith, refusing to let the cosmos be simpler than it is. New machines are readied to map the invisible bones of creation, and running beneath all of it, steady as a heartbeat, is the question that has turned a settled science into a living frontier. The universe is expanding faster than it should, and we do not yet know why. That sentence is not an ending. It is a beginning wearing the costume of an ending, the way these things always do. Somewhere in the unwatched middle of cosmic history, some actor we have never seen is shaping the story, and the whole enterprise of modern cosmology has bent itself toward finding out who. When the answer comes, and one day it will not diminish the universe. It has never once worked out that way. It will make the cosmos larger, and older or younger in ways we cannot yet guess, and stranger than the map we drew, and, if the long pattern of this science holds, more beautiful than anything we have so far allowed ourselves to imagine. Until then, The sky keeps its secret in plain sight, written in the light of a billion galaxies, waiting for eyes clear enough and minds humble enough to finally read it. Let us return, for a while, to the ladder itself, because the more you understand how it is built, the more you appreciate why its verdict has proven so unshakable. The whole structure rests on a chain of trust, each link calibrated against the one beneath it, and a single weak link anywhere along the chain could, in principle, throw off everything above it. That is why critics reached for the crowded pulsing stars as the likely flaw, and why the newest telescope was aimed at them with such anticipation. But the chain does not begin with those stars. It begins even closer to home, with objects whose distances can be measured by pure geometry, by watching how their apparent position shifts ever so slightly as our planet swings from one side of its orbit to the other. That shift, tiny beyond ordinary comprehension, gives a distance that depends on nothing but angles and the known width of our orbit, the cleanest ruler in all of astronomy. Anchor the pulsing stars to those geometric distances. Anchor the exploding stars to the pulsing stars, and reach outward into the deep field of galaxies. And every rung inherits the honesty of the first. When the new telescope confirmed the pulsing stars, it was confirming a link near the base of the chain, and finding it sound only made the whole ladder more trustworthy, not less. The number held because the structure holding it up was stronger than its critics had hoped. And yet the rival astronomer's caution was not misplaced, and it points at something genuinely subtle. Her worry was never that the ladder was carelessly built. It was that different choices of which stars to trust, which galaxies to include, which corrections to apply, could nudge the final answer in small but meaningful ways. And that until those choices are fully understood, a sliver of doubt must remain. Her decision to lean on ancient red giants and other markers found in the calm outskirts of galaxies, far from the crowded cores, was an attempt to build a parallel ladder that sidesteps the very crowding problem that started the debate. That her parallel ladder returned numbers scattered across the middle ground, some near the ancient light value, and some near the direct measurement value, is itself a kind of result. It says the answer may depend, delicately, on exactly how you climb. And that is not a comfortable thing to hear about a measurement the whole field has leaned on for a century. It suggests the ladder may be trying to tell us something not only about the universe, but about the limits of our own methods. A reminder that even our finest rulers have grain in the wood. This is where the drama becomes genuinely subtle, because there are really two possibilities tangled together, and the field has not yet fully separated them. The first is that the ladder is essentially correct. The number really is close to 73, and the disagreement with the ancient light is a true feature of the universe pointing at missing physics, somewhere in the unwatched middle. The second is that some unrecognized flaw, hidden in the way we build the ladder or read the exploding stars, is quietly inflating the direct measurement, and the true value is lower, closer to what the ancient light predicts. The first possibility would mean the framework needs new ingredients. The second would mean our measurements need refinement, but the framework may survive. Distinguishing between them is one of the central tasks of the field right now, and it is why the future instruments matter so much. Cleaner geometric distances, larger samples of exploding stars, independent methods that do not rely on the ladder at all. Each of these is a way of asking the universe the same question from a new angle, hoping the answers will finally converge on a single truth. And there are independent methods, which is what makes the persistence of the tension so striking. Astronomers have found ways to measure the expansion that bypass the ladder entirely. Some use the ripples frozen into the distribution of galaxies, the faint preferred spacing left over from those primordial sound waves, as a standard ruler stretched across cosmic time. Some use the way massive objects bend and delay the light of distant flickering sources behind them, timing the delay to extract a distance. Some use the gravitational shivers of colliding dead stars, ripples in space itself that carry their own intrinsic scale. Each of these methods has its own strengths and its own uncertainties, and each is being pushed toward the precision needed to weigh in decisively. So far, they have tended to land between the two headline numbers, not sharp enough yet to settle the matter, but sharpening year by year. When one of them, or several together, finally reaches the precision of the latter and the ancient light, it will either confirm the tension beyond any escape, or reveal the hidden flaw that dissolves it. Either outcome would be a landmark. The universe is being interrogated from every direction at once, and it is only a matter of time before it stops being able to keep its secret. It is worth dwelling on how recent all of this is, because it changes how you feel about the moment we are living in. A generation ago, the disagreement simply could not have been detected. The measurements were too coarse. The error bars on both the ancient light and the latter were wide enough to overlap, and everyone assumed that as precision improved, the two would settle onto a single agreed value. That is what usually happens as measurements sharpen. Instead, the opposite occurred. The more precise each method became, the more firmly each locked onto its own distinct number, and the overlap that once let everyone relax steadily vanished. The tension did not fade with better data. It hardened. That hardening is the single most important fact of the entire affair, because a discrepancy that grows sharper as the measurements improve is exactly the fingerprint of real physics, rather than sloppy work. Errors tend to shrink and blur as you refine your tools. Truths tend to come into focus. What we are watching come into focus is a genuine gap between the universe's youth and its old age. And it is coming into focus precisely because we have never before been able to see either end so clearly. Turn back now to the deep field, to those galaxies caught in the first few 100 million years, and consider what they imply about the pace of creation. In the framework's telling, the young universe should have been a place of slow beginnings, of small structures gradually gathering, of gas cooling patiently in the wells of unseen matter before finally kindling into the first faint stars. Instead, the telescope keeps returning images of a universe in a hurry, building bright and massive galaxies with startling speed. Even setting aside the disguised black holes, the surplus of early massive galaxies suggests that star formation in that first era was more efficient, more vigorous, more productive than anything we see in the calmer universe around us today. It is as though the young cosmos burned hotter and brighter than its later self, converting its raw material into stars with an urgency it would later lose. Why the early universe should have been so much more fecund is a genuine puzzle, and the answers being explored reach into some of the deepest questions about how the very first stars formed, and how quickly the invisible scaffolding assembled itself out of the smooth beginning. The very first stars are a mystery in their own right, and they sit at the center of this question. They formed from gas that contained none of the heavier elements that pepper the universe today. Gas that was almost purely the lightest elements forged in the first minutes of existence. Without those heavier elements to help it cool and fragment, that primordial gas may have collapsed into stars far more massive than any that form now. Monstrous suns burning with ferocious brilliance and living fast, violent lives before exploding and seeding their surroundings with the first heavier elements. If those first stars were as massive and as brilliant as some models suggest, they could have driven the rapid growth of the earliest galaxies, flooding them with light and energy and enriching them quickly enough to build the next generation of stars at a furious pace. The impossible early galaxies may be, in part, a message about those first stars, a signal that the opening chapter of cosmic history was more dramatic and more rapid than the gentle picture allows. We have never directly seen an individual first-generation star. They lived and died long before any light we can currently gather set out toward us. But their fingerprints may be written into the surprising maturity of the galaxies the great telescope keeps finding. And reading those fingerprints is one of the most tantalizing tasks the new era of observation has opened. The grand early spiral, serene amid the expected chaos, sharpens the puzzle in a different direction. Spiral structure is delicate. It requires a galaxy to settle into a smooth, rotating disk, and to remain undisturbed long enough for graceful arms to wind through it. In the early universe, where the model expects frequent collisions and violent mergers, such delicacy should be almost impossible to maintain. Any spiral pattern should be torn apart before it could fully form. Yet there it was, a mature and orderly pinwheel, gliding through an age of supposed turmoil. The astronomers who found it wrestled with what it meant, and the possibilities were both unsettling to the standard picture. Either the galaxy had gathered its enormous mass in a far more orderly way than the model expects, avoiding the disruptive collisions that should have defined its era, or it had formed nearly all of its stars in place, quietly, without the mergers that normally assemble such giants. Either way, the young universe was capable of building calm, structured, mature objects far earlier than the framework foresaw, and it was doing so alongside the turbulent, clumpy adolescence that a separate survey found in the very same epoch. The coexistence of the serene and the chaotic in the same early moment is a scene the model was not written to describe, and it hints that the rules governing how structure forms may be richer and more varied than we assumed. And then there are the shapes, those long, elongated forms stretched like grains of rice through the deep field, which may be the quietest but most far-reaching clue of all. To understand why, you have to appreciate that the shape of a young galaxy is molded by the invisible scaffolding it grew within, and the scaffolding is molded, in turn, by the nature of the unseen matter. If that matter is the cold, clumping kind the framework assumes, it pools into roughly spherical wells, and galaxies born inside those wells should tend toward rounded, compact forms. Long, slender galaxies are hard to make that way. But if the unseen matter is lighter or gentler, if it behaves less like a swarm of cold particles, and more like a smooth, flowing field, then it does not fragment into as many compact clumps. Instead, it drapes itself into long, smooth filaments, and galaxies form strung along those filaments, like beads on a thread, drawn out into exactly the elongated shapes the telescope observed. The shapes, in other words, may be a direct readout of the fundamental nature of the most abundant matter in existence, a fingerprint left on the young galaxies by the very substance, whose identity has eluded us for decades. If that reading holds up, it would be one of the most consequential clues in the entire modern history of the subject, because it would point away from the cold picture that has anchored cosmology and toward something new. All of these threads, the runaway expansion, the precocious galaxies, the serene early spiral, the elongated shapes, the missing clumpiness, could in principle be unrelated, a collection of separate puzzles that happen to have surfaced in the same era of observation. But the more compelling and more unsettling possibility is that they are connected, that beneath them runs a single unrecognized truth about the universe, and that each anomaly is a different shadow cast by the same hidden object. Perhaps the nature of the unseen matter is not what we assumed, and that single change ripples outward to reshape how galaxies formed. how their shapes turned out, how clumpy the cosmos became, and even through its influence on the early universe, how fast expansion proceeds today. Perhaps the mysterious outward pressure behaves differently than we modeled, surging early or shifting over time, and that single change reconciles the two expansion numbers while rearranging the early cosmos. We do not yet know whether one cause underlies many symptoms, or whether we are facing several independent mysteries at once. But the search for a single unifying explanation is one of the great intellectual adventures of the present moment, and the prize for finding it would be nothing less than a new and truer picture of everything. There is a discipline in how the best of these researchers hold all this uncertainty, and it is worth admiring. They do not overclaim. They do not announce revolutions before the evidence demands them. When a correction like the disguised black holes comes along and rescues part of the framework, they accept it honestly and adjust, even when a more dramatic story would have made better headlines. And when a stubborn remainder persists after the correction, they refuse to pretend it away. This is the quiet machinery of science working as it should, neither clinging to the old picture out of comfort, nor abandoning it out of excitement, but following the evidence with patience wherever it leads. The framework is being tested at its foundations, and the people testing it are precisely the people who built and love it, which is exactly as it should be. There is no glory in defending a theory that the sky has outgrown, and no glory in tearing down a theory that still explains so much. The glory, if there is any, lies in finding the truth, and the truth is proving harder won, and more surprising than anyone expected. It helps to remember that the framework's greatest triumphs remain intact even as its fractures multiply. The faint ancient light still fits the model's predictions with a precision that remains one of the crowning achievements of the physical sciences. Its every ripple and pattern accounted for. The cosmic recipe of the lightest elements, forged in the first minutes of existence, still matches the framework's forecast to remarkable accuracy. A prediction made from pure theory and confirmed by observation across the whole sky. The grand web of galaxies, its filaments and voids stretched across billions of light years, still emerges from the model's equations in a way no rival can yet reproduce. These are not small successes. They are among the most impressive predictions ever made about the physical world, and they are the reason the framework cannot simply be discarded. Whatever new ingredient eventually explains the fractures will have to preserve all of these triumphs while curing the ailments, and that is an extraordinarily demanding requirement. It is why the search is so hard, and why the eventual answer, when it comes, is likely to be profound. Anything that can honor the framework's successes while resolving its failures will not be a minor patch. It will be a genuine deepening of our understanding of reality. The mysterious outward pressure that drives the accelerating expansion deserves a final, longer look, because it is in many ways the deepest mystery of all, and it sits close to the heart of the expansion problem. This pressure accounts for the majority of the contents of the universe, more than the visible matter and the unseen matter combined, and yet we cannot say what it is. We know it through its effect. Space is not merely expanding, but expanding ever faster, as though something is pushing outward against the pull of gravity across the whole cosmos. We have given this something a name, but the name is a placeholder, a label pasted over our ignorance. We cannot capture it in a laboratory. We cannot point to a particle or a field and say, "There, that is the thing." We know only that it is there, that it dominates the universe, and that it shapes the destiny of everything. And if its behavior is even slightly different from what the framework assumes, if it was stronger in the past or is changing now, it could be woven into the very heart of the expansion problem. Some of the future observatories are being built expressly to study it, to trace its influence across cosmic time, and to test whether it has truly been constant, or whether it too holds a secret that would rewrite the framework. To confront the expansion problem honestly is, in part, to confront how little we truly understand about the dominant ingredient of our own universe. Step back far enough, and a striking picture emerges of just how much of the cosmos remains genuinely unknown. The matter we can see, the stars and gas and dust, and everything built from them, including ourselves and our world, makes up only a small sliver of the total. A larger portion is the unseen matter whose nature we are still debating. And the largest portion of all is the mysterious outward pressure we cannot explain at all. In other words, the overwhelming majority of the universe is made of things we do not understand, detected only through their gravity and their effect on the expansion of space. The framework describes how these unknown ingredients behave with great success, but it does not tell us what they are. And the current crisis is, at its root, a sign that even our description of their behavior may be incomplete, that the placeholders we have used are hiding physics we have not yet discovered. When you hold that thought clearly, the tension over a single number stops feeling like a technical quarrel and starts feeling like what it truly is, a crack through which we may finally glimpse the vast unknown that makes up most of reality. The people watching these cracks are not frightened by them, and that attitude is itself a kind of wisdom. They understand that a theory which explained everything, with no loose threads and no surprises, would in a sense be a dead end, a finished story with nothing left to discover. It is the anomalies, the stubborn refusals of the sky to match the map, that keep the science alive and pull it forward toward deeper truth. Every great advance in the understanding of the cosmos began as an anomaly that would not go away. A small, persistent disagreement between prediction and observation that eventually cracked open into a whole new vision. The current fractures have that same feel, the same stubborn persistence, the same refusal to be explained away by better data. And so the mood among those closest to the work is not dread, but a kind of electric anticipation. The sense of standing near a door that is beginning to open, unsure of what lies beyond it, but certain that it is large. What lies beyond it, whatever it is, will be found the way everything in this science is found. Patiently, carefully, through the accumulation of evidence and the willingness to be wrong. The great eye in the dark will keep gathering light, night after night, adding galaxy after galaxy to the record, sharpening the picture of the early universe until its surprises can no longer be dismissed. New observatories will map the invisible geometry of the cosmos on scales never before attempted, testing the nature of the unseen matter and the behavior of the mysterious pressure with unprecedented reach. Cleaner rulers, larger samples, independent methods, all of them are being brought to bear on the same set of questions, and the answers are drawing closer. It may take years, it may take decades, but the direction is clear, and the momentum is real. We are closing in on the missing piece, the uncounted ingredient, the unmodeled process that will finally reconcile the runaway expansion and the impossible galaxies and the elongated shapes and the missing clumpiness into a single coherent picture. And when that piece is finally found, the universe will not become smaller or duller or more ordinary. That has never once been the outcome of these upheavals. Every time our understanding of the cosmos has been forced to grow, the cosmos has grown with it, revealing itself to be vaster, older or younger in unexpected ways, richer and stranger than we had allowed ourselves to believe. The discovery of the unseen matter did not shrink the universe. It revealed that most of it was invisible. The discovery of the accelerating expansion did not tame the cosmos. It showed that its deepest engine was a mystery we had never suspected. The current crisis, whatever it turns out to reveal, will almost certainly follow the same pattern, expanding our sense of what is real rather than contracting it. The fractures in the framework are not signs of failure. They are the growing pains of a species learning to read the universe more clearly than ever before, reaching the edge of its knowledge, and, instead of stopping, leaning forward to see what lies beyond. For now, the question hangs in the air, unanswered and luminous. The universe is expanding faster than our finest theory says it should, and the impossible galaxies of the early cosmos are stranger and more mature than any model foretold, and the invisible matter that shapes everything may not be what we assumed, and the outward pressure that dominates all of existence remains a name pasted over a mystery. We do not know the answer, but we know we are looking at the sky more clearly than any people who have ever lived, with instruments of astonishing power and minds honest enough to admit what they do not understand. And somewhere in the light streaming down from a billion galaxies, in the faint glow of the cosmic dawn, and the stretched shapes of the earliest structures, and the precise disagreement between two carefully measured numbers, the answer is waiting, written in a language we are only beginning to read. When we finally read it, the map of everything will be redrawn, and the universe revealed will be larger and stranger and more beautiful than the one we thought we knew. Until that day comes, the watching goes on, the questions stay open, and the sky keeps its secret in plain view, patient as light, waiting for us to catch up. There is one more dimension to this story that rarely gets told, and it concerns the sheer improbability of even being able to ask these questions. The measurements at the heart of the crisis depend on chains of physical coincidence, so fortunate that they can feel almost designed for discovery. The pulsing stars keep honest time only because of a delicate balance in their outer layers, a rhythmic swelling and shrinking that happens to encode their true brightness. The exploding stars flare to nearly identical peaks, only because they detonate when a dead stellar core crosses one specific, universal threshold, the same everywhere in the cosmos. The ancient light survived, unabsorbed and undistorted, across nearly the entire age of the universe, so that we could read the conditions of the cosmic dawn from it. Remove any one of these gifts, and the latter collapses. The map of the early universe goes dark, and the crisis could never have been detected at all. That we possess all of them at once, and instruments precise enough to exploit them, is what allows a species on a single small world to feel the disagreement between the youth and the old age of the entire universe. The crisis exists, in a sense, because the cosmos is legible, because it left us just enough honest signals to measure it two different ways, and notice that the answers do not match. Think about what it means to compare those two answers. On one side stands a number extracted from the faint imprint of the cosmic dawn, carried forward across billions of years by the machinery of the framework, a prediction of how fast space should be stretching now, built on the earliest light in existence. On the other stands a number read directly from the nearby universe, from the pulsing stars and the exploding stars and the fleeing galaxies. A measurement of how fast space is actually stretching now, owing nothing to the deep past. When those two numbers agreed, as everyone long assumed they would, it was a quiet confirmation that the framework connected the beginning to the present seamlessly, that the whole vast story hung together. When they refused to agree, it meant the seam between the beginning and the present had split, that the framework's account of the journey from the cosmic dawn to tonight is missing something. That is the real weight of the disagreement. It is not a quarrel about a decimal. It is evidence that the bridge our theory builds across 14 billion years has a hidden gap in the middle. And something we have not yet named is standing in that gap, altering the flow of cosmic history in a way we are only now beginning to feel. The way this crisis is likely to resolve is instructive to imagine, because it will almost certainly not be a single dramatic moment of collapse. It will be a slow convergence, a gathering of independent lines of evidence, until the weight of them tips the balance decisively one way. Perhaps the geometric distances to the pulsing stars, measured with ever greater purity, will confirm the latter beyond any doubt, forcing the framework to accept new physics in the unwatched middle. Perhaps a subtle flaw in the exploding stars will be uncovered, some quiet variation in their brightness that inflates the direct measurement, and the two numbers will slide back into agreement, sparing the framework at the cost of humbling the latter. Perhaps the independent methods, the frozen ripples in the galaxy distribution, and the time delays of bent light, and the shivers of colliding dead stars, will sharpen until they point unambiguously at one value or the other. Whichever way it goes, the resolution will be earned through accumulation, through the patient piling up of evidence, until the answer becomes undeniable. That is how these things end, not with a shout, but with a slow and irresistible convergence toward truth. And whatever that truth turns out to be, it will carry consequences far beyond the single number. If the higher value stands and new physics is required, then the framework that has ruled cosmology will have to make room for a new ingredient, some early surge of pressure, or shifting behavior of the dark components, and the textbooks will be rewritten to include it. If the lower value prevails, and the latter is found wanting, then the methods astronomers have trusted for a century will need rebuilding, and a new generation of even more careful measurements will rise in their place. Either outcome reshapes the field, and running alongside the expansion problem, the impossible galaxies and the elongated shapes, and the missing clumpiness will demand their own reckonings, each one potentially pointing at the same hidden truth, or at several distinct ones. The coming years may bring not a single revolution, but a cascade of them, each anomaly resolving into a new piece of understanding, until the picture of the cosmos we hold a decade or two from now looks meaningfully different from the one we hold today. It is a rare privilege to be alive at a moment when the deepest map is being redrawn. For long stretches of history, the fundamental picture of the cosmos seemed settled, the main work being refinement within an accepted frame. We are not in such a stretch now. We are in one of the rare intervals when the sky is actively refusing to obey the story we told about it, when the measurements have outrun the theory, when the next great reframing of reality has not yet been written and lies open before us. The people closest to the work feel it as a kind of charged expectancy, the sense that they are living through a hinge in the history of their science, one of those moments that later generations will look back on as the beginning of a new understanding, and the rest of us get to watch it unfold in something close to real time, to feel the tension tighten and the anomalies multiply and the instruments sharpen, and to sense, even from a distance, that something large is stirring at the edge of what we know. None of this diminishes the ordinary wonder of simply looking up. The same universe that hides these profound mysteries also fills our night sky with light that has traveled unimaginable distances to reach us. Light from stars and galaxies whose true nature we are still struggling to understand. When you stand beneath a dark sky and let your eyes adjust, the faint band of our own galaxy arching overhead, you are looking at the same cosmos that is confounding the finest measurements ever made. The disagreement over its expansion, the impossible early galaxies, the invisible matter and the mysterious pressure, all of it is written into that quiet, glittering expanse above you. The mystery is not somewhere far away and abstract. It is directly overhead, in the light falling on your upturned face, waiting to be understood. And there is a strange comfort in that, in knowing that the grandest unsolved questions of existence are not hidden in some inaccessible vault, but are shining down on all of us, freely, every clear night, inviting anyone who cares to wonder. So the story remains unfinished, which is exactly as it should be. The framework still stands, wounded but not fallen, explaining vast reaches of the cosmos, with a precision that remains one of humanity's proudest achievements, even as its fractures spread and refuse to close. The two numbers still disagree, sharper now than ever, pointing at physics we have not yet grasped. The early universe still hands us galaxies too large, and too orderly, and too strangely shaped for any model to have foreseen. The invisible matter still keeps its identity secret, and the mysterious pressure still dominates everything while explaining nothing. And the great eye in the dark still watches, patient and unblinking, gathering the evidence that will one day force the answer into the open. We do not know what that answer will be, but we know the shape of the search, and we know the character of the people conducting it, and we know the long history of their science, which has taught us that every crisis is a door, and every door has led to a larger room. The universe is telling us, in the clearest language it has, that our map is incomplete. And rather than fear that message, we should be grateful for it, because it means the greatest discoveries are not behind us, but ahead, waiting in the light of the galaxies, in the faint glow of the cosmic dawn, in the precise and stubborn disagreement between two carefully measured numbers. The reckoning is coming, and when it arrives, the universe it reveals will be stranger, and larger, and more beautiful than the one we thought we had finally understood.